Welcome back to another video. In today's video, we'll talk about graphical and algebraic interpretation of limits, followed by discussion of a very useful rule when it comes to determining limits, which is L'Hopital's rule. So, starting off with looking at limits graphically, let's look at this function over here. So, this is our function f of x, and we'll be using this throughout the question. Before I introduce you with the notation and the way limits work, let's just first of all look at some random questions regarding this function. So when x is 1, when x has the value 1, what is the value of f of x on this function? So when x is 1, I can see clearly that f of x is 5. Similarly, when x is 6, the value of f of x, as can be seen, is 3. Please bear in mind that in this particular case, when x is 6, f of x is not 1 because this is hollow. So basically, there's a discontinuity in the graph at this point. So when x is 6, the value of f of x is not 1, but it's 3. Now, these questions, these very same questions, can also be phrased in a different way. So, what is the value of this? F of 1. Now, f of 1 has the value of 5 because it's the same question as the first one. It's the same question as this. So essentially, whatever is in the bracket is the value of x. Let's try and understand this using one more example. So when what is f of minus 2? So the bracket basically contains the value of x. So we have to find the corresponding value of the function when x is minus 2. So looking at it from the graph, we can see that the value of f of x when x is minus 2 is 2. So the answer to this is 2. I hope this part of the lecture is clear because what I'm going to do next is introduce the notation and the concept of a limit. Therefore, understanding this is important. Now, moving on, I can be asked this question: limit x approaches 6 f of x. Now, in order to understand what this notation is, I will just write down here what it actually means and how it's read. So this is read as, what is the limit of the function as x approaches 6. So this is how we read this particular part. What is the limit of the function as x approaches 6? Now, for a beginner, this would mean that, as x approaches 6, the value of f of x should be 3, as we just saw previously. So this should be 3. But we do not look at limits the normal way. We will not just look at the value of x as 6 and find the value of y. That's now not how it works. So, in order for me to solve this question correctly, I will have to look at x as 6, but I'll have to look at it slightly to the left and then slightly to the right. So what I mean is, I don't have to look at 6 exactly on the x-axis. I'll just look at a point which is very close to 6, like 5.99. And then I'll see what is the corresponding value of y when x is 5.99. As you can see, the value is approximately 1. So when I look at 6 from, so when I look at x equals to 6 from the left, then f of x is 1. Similarly, I will now look at what the value is when I look at 6 from the right. So let's suppose I look at 6.001 on the x-axis and find its corresponding y value. As you can see, the corresponding value is very close to 1. So when I look at x equals to 6 from the right, then f of x again is 1. So the limit as x approaches 6, the limit of the function as x approaches 6 is 1 and not 3. I repeat, when you're talking about limits, you don't look at the exact x value. You look at one value which is slightly to the left of that x stated value and one value to the right. This can only be further clarified if we look at more examples. So, let me change the question and let me ask you, what is the limit of f of x as x approaches, let's say, minus 3? Now, I've been given with a value of x which is minus 3. If I look at minus 3 on the graph, if I look at the value of x as minus 3 on the graph, there's nothing that y has. So when x is minus 3, there's nothing on y because the graph is hollow here. So when x is minus 3 exactly, f of x has no value. So what should the limit be then when x approaches minus 3? As done previously, what we'll do is we will look at a value to the left of minus 3, which is very close to minus 3. And when we do that, the value of y is very close to 1. So when x is minus 3 from the left, then f of x equals to 1. Similarly, we'll look at a value which is very close to negative 3, but from the right. So when x is negative 3 from the right, or x approaches negative 3 from the right, the value of f of x is still 1, which makes us believe that the limit as x approaches negative 3 is 1 for this function. Now, there will be times when limits do not exist. So let's have a look at an example where this happens. So, just to make everything less clustered, I will erase this. And let's now try and answer this question first. So when we have f of 2, meaning when the value of x is 2, then the exact value of the function is 1. But what about the limit as x approaches 2? So how do we read this? This is read as, what is the limit of the function when or as x approaches 2? So I'll not be looking at x exactly at the point 2. I will look at it slightly from the right. So when I look at it slightly from the right, the value of f of x is very close to 1. So when I look at x equals to 2 from the right, then f of x equals to 1. But Now let's see what happens when I look at x equals to 2, but slightly from the left. When I look at f of when I look at x equals to 2 from the left, the approximate value that I get, so x equals to 2 from the left gives me an f of x value of 2. Now, as you can see, when I looked at it from the right, the value was 1 of f of x. But when I looked at it from the left, the value of f of x was 2. In this case, the answers are not the same. So when I look at 2 from the right, the answer is 1. When I look at 2 from the left, the answer is 2. The answers are not the same. And when this happens, we say that the limit does not exist. So, summarizing our understanding, when we are asked to, so the summary so far is when we're asked this question, let's suppose what is f of 2, then we have to look at the exact value of 2, and then we have to find what the value of f of x is. But when we have to find limit of f of x as x approaches 2, then we have to look at x equals to 2 from the right and x equals to 2 from the left. And only if these two values are the same, then the limit exists. Otherwise, the limit does not exist, as discussed in the examples. Some quick questions. So, in this graph, if you look at the value of x when x is negative 2, the exact value of f of x when x is negative 2 is 2. But the limit as x approaches negative 2 of f of x would be slightly different, or it might not exist. So let's look at minus 2 from the right first. If I look at minus 2 from the right, slightly from the right, the value I get is, so x equals to minus 2 from the right gives me a value of 4. And x minus 2, if I look at it from the left, then the value of f of x is minus 1. So from the left, the value of f of x is negative 1. So these two answers are not the same. The value of f of x is not the same, which means this limit does not exist. Now, as stated at the start of the video, we'll also be looking at algebraic interpretation of limits. So let's look at a few expressions of which we have to find the limit of. So for instance, I have to find the limit of this expression that I will paste here. Now it's not a graph as we've been discussing, rather it's an expression. So we can see that the value of x given here is 2. One way to do this would be to simply substitute 2 in place of x. So the numerator will become 2 squared minus 2 over 2 minus 2. If we solve this, we will get 0 over 0, something which has no interpretation so far. Now, the idea here is when we are given an expression along with the value of x, we will not simply put in the value of x into the expression. Rather, we will first of all look to simplify the expression. So let's simplify this expression and see what happens. The numerator can be factorized, and we know that -2 will be split as, so we need two numbers which multiply to give -2 and add or subtract to give -1. So the middle term breaking for this would look like this, over x minus 2. So the denominator stays as it is. Now further simplifying the numerator, we get x as common, leaving us with x minus 2, and plus 1 common, leaving us with x minus 2 over x minus 2. Further simplifying the numerator, we get x minus 2 times x plus 1 over x minus 2. Now this can be simplified, and all we're left off with is x plus 1. So the expression given in the question has now become equal to x plus 1. So I can just write x plus 1 here. Now all we have to do is, now we can plug in x equals to 2 in the expression, giving us 2 plus 1, which is 3. So the answer to this is 3. The key in finding limits of algebraic expressions is to simplify the expression first. That is extremely important. For instance, let's look at the limit over here. So for example, we have x plus 3x squared over x squared. Now we have to find the limit of this expression as x approaches infinity. If we simply plug in infinity for x, we'll end up with something like infinity over infinity, something that makes no sense for now. But what we could do is we could simplify this first, leaving us with x over x squared plus 3x squared over x squared, which further gives 1 over x plus 3. Now we can plug in x as infinity into this expression, leaving us with 1 over infinity plus 3. Now 1 over infinity is 0. In fact, anything over infinity is 0. So 0 plus 3 will give me 3. So the limit of this expression as x approaches infinity is 3. Remember the fact that simplifying the expression is greatly and extremely important. Let's look at one more example before we look at the L'Hopital's rule as stated, as mentioned at the start of the video. So let's suppose we have this to find. Now it's asking me to find the limit of this expression as h approaches 0. So if I just simply put h0 in this expression, I'll end up with 0 over 0, which again makes little sense. So the key is to simplify this. Simplifying this means that I'll open the parenthesis, leaving me with 9 plus 6h plus h square minus 9 over h. Now 9 and 9 can cancel, which then give me 6h plus h square over h. Now I can take h common, which gives me 6 plus h over h. H and h cancel. Now I can use h equals to 0, which was the limit given, leaving me with 6 as the answer. So far, we've looked at graphical and algebraic interpretation of limits and how to find limits graphically as well as algebraically. Now, let's look at a rule which is known as the L'Hopital's rule, and let's see how it works. So, there will be questions where one is supposed to find limits of expressions which hardly make any sense and which cannot be further simplified as well. So let's suppose we have x squared plus x minus 6 over x. Now suppose we have this expression to find the limits of, and as you can see, this cannot be further simplified, and if I put x0, I will end up with minus 6 over 0, which does not really make much sense. So the L'Hopital rule says that if you have to find the limit of any function, which is exact actually a denominator combined with a numerator, then what we can do is we can differentiate both the functions separately and then use the value of the limit given. So I repeat, L'Hopital rule says if you have an expression which is a fraction having a function of x in the numerator as well as a function of x in the denominator, and something which cannot be simplified, then one could always differentiate both functions separately and then put in the limit given. So if we apply this rule here and differentiate this, we'll end up with 2x plus 1 minus 6 over 1. Now, if I further simplify this, this would give me 2x minus 5. And if I put 0 for x now, the limit would be negative 5. But there are some limitations of the L'Hopital's rule. This generally works if initially in our question we have, first of all, a fraction, and if we put the limit in our original function, we end up with something like 0 over 0 or infinity over infinity, etc. Otherwise, L'Hopital rule cannot be applied. So I repeat, L'Hopital rule can be applied if in our original expression, so this is our original expression, and if I put the limit in my original expression and I end up with 0 over 0 or infinity over infinity, then L'Hopital rule can be applied. So let me talk about an example. Suppose I have to find limit as x approaches 2 of x squared minus x plus 6 over x minus 2. Now in this question, if I put if I put 2 for x, this is plus, I will end up with 2 squared plus 2, and this is supposed to be minus 6 and not plus 6, please note. 2 squared plus 2 minus 6 over 2 minus 2. I'll end up with 0 over 0. So in my original expression, if I use the limit given, I end up with 0 over 0. So which means L'Hopital's rule can be applied and I need to differentiate both, leaving me with 2x plus 1 over 1. And all I have to do is now plug in the value 2 and I'll get the answer. In our next video, we can further talk about the applications of L'Hopital's rule. Thank you for watching.